Morning, students. Next, very important topic: statistical inference. Statistical inference can be broadly classified as two ways. First one is theory of estimation. Second one, testing of hypothesis. These two are very important for the nationwide and regional-wide examination point of view. It's very important topics. More weightage to the nationwide university examination. So now, theory of we are going to discuss about the theory of estimation. So theory of estimation is classified as point estimation and interval estimation. First, we have to take the point estimation. So before taking this point estimation, so what is the objective of the theory of estimation? The objective of the statistical analysis is to be estimate the unknown population characteristics, usually known as parameter. So already explained what is the parameter in the last videos. Parameter means population constant or population characteristics. In this so theory of estimation techniques, using the techniques, we have to estimate the unknown population parameter and to infer about the parameter. So this is the objective of the uh, theory of estimation. So here I am taking the one example to give the correct meaning of the theory of estimation. For example, so here is a population. So several samples are drawn from this population. Population parameter usually denoted as theta. Theta belongs to parametric space. I will give the complete meaning of the parametric space. So now here we have to estimate the unknown population characteristics theta. It is called parameter. It is called parameter. Is called parameter. Several samples are drawn from this one. Sample 1, sample 2, sample n here. Now here using the sample statistic. Statistic means a function of sample observations. So here is mainly we have to the statistic are denoted as t. T is a function of sample observations. Is a random variable. T of x1, x2, and so on xn. x1, x2, and so on xn. The function of sample observations. Using this t, so we have to estimate the theta. Now, for example, Vijayawada city is a population. Vijayawada city treating as a population. So we are very much interested to find out the estimate the average marks. Average marks in a particular subject. In a particular subject. In a particular subject. So now total population enumeration is a very typical one. In this case, we have to draw the one sample. So we have to collect the one. We have to select the one college from this Vijayawada city. So now here we have to collect the data in that collect the marks in that particular subject. The marks like this x1, x2, xn. So now here using these sample observations, form a statistic here. That is t is equal to t of x1, x2, and so on, xn. So now here this t is here average marks in a particular subject denoted as theta here. So using this t value, we have to estimate the theta value. So this is theta is the population so mean. This t is the sample mean here like this. So we have to estimate the population mean using the sample mean. So this is the importance of theory of estimation. So that researcher or investigator so guess the hypothetical value of population parameter. After that, this hypothetical value is accepted or rejected here. Using the testing hypothesis techniques, that hypothetical value is maybe accepted, may not be accepted here. So that is the next part here. So in this part, we have to only give the true value of the population, unknown population characteristic. A function of sample observations is called statistics. Statistic. If this statistic is used to express a particular value of a parameter, it is called estimator. It is called estimator. T is called the estimator. T is called estimator or point estimator or point estimator. Point estimator. So now here the method of deriving such a function of sample observations. to guess the population, uh, unknown value, population unknown characteristics is known as a point estimation. This is the definition of the point estimation. The method of deriving such a function of sample observations to guess the population unknown characteristics is known as point estimation. So here we have to, before taking these concepts here, first of all, we have to define the parametric space. Parametric space means the set function, so denoted as H circle. So this is called a parametric space, which is the set of all possible values of theta. It is called the parametric space. Parametric space, like a sample space, which is the set of all possible values of theta. For example, x follows n of mu comma sigma square. So then the parametric space H circle is equal to mu comma sigma square. The parametric space limits here, this mu and sigma square belongs to parametric here. The mu lie between minus infinity to plus infinity. Sigma always greater than 0. So never be 0, never be negative here. Sigma is always standard deviation or variance. Sigma square or here. Sigma square also is greater than 0. Lie between 0 and infinity. Lie 0 and infinity. So now another example, x follows binomial n comma p. Binomial population n comma p, the parametric space H of p is lie between 0 and 1, strictly lie between 0 and 1. Both are excluding values. So another example here, one more example, x follows Poisson lambda, parametric space H circle of lambda. Lambda is always greater than 0. So now lambda belongs to parametric space. Lambda belongs to parametric space. Similarly, one more example, x follows exponential distribution, expo of lambda, expo of theta. Now the H circle, the parametric space of theta is always greater than 0. Theta belongs to parametric space. This is the population parameters. Lambda, theta, p, mu, sigma square are all population parameters, population constants. Now, let x1, x2 be a set of n random sample observations from a population having PD of f of x comma theta. Theta belongs to parametric space, already defined. The problem is to estimate the parameter theta using the set of sample observation is called a statistic. So using a set of sample observations. Let the g of x be a function of sample observations. G of x or t. So different notations may be used. So to define this set of function of sample observation, this function g of x provide precise information about the parameter theta. The principle of identifying the sample function which will provide precise information about parameter theta is known as the method of estimation. This is the definition of the estimation. So now here the population parameter here is the population PDF is f of x comma theta. This theta belongs to h. Theta belongs to h here. Now here draw the one sample here and consider the sample function x1, x2 and so on, xn. It is called g of x. Using this function, we have to estimate the, this is statistic. This is called a statistic. It is called statistics. Using the statistics, we have to estimate the parameter theta. Estimate the parameter theta. This process here is the principle of identifying the sample function. The principle of identifying the sample function, which will provide precise information about the population, unknown population parameter theta, known as the method of estimation. The estimation functions are referred to as estimators. Estimating functions are then referred to as estimators. So this is the introduction of the theory of estimation. So next here, very, very important one, criteria. So total chapter depends upon this criteria of a good estimator. So here is what is good estimator here. So any estimator, any statistic satisfy all these four criteria, four properties. That estimator is called good estimator. So actually these four are the psychological word: unbiasedness, consistency, efficiency, sufficiency. So human being as unbiased person or consistent person, efficient person, or sufficient person, that person is called a good person in the good citizen in the society here, or good policeman, good politician, good doctor, good mechanic, everything here. All the good citizen means here that the citizen must satisfy all these four important properties. Similarly here, in this case here, in statistical theory, so we have to estimate the unknown population parameter theta using the sample function here. That sample function is called statistics. That statistic satisfy all these four properties. That statistic is called a good estimator. Using that estimator, we have to estimate the unknown population parameter theta. How to give the importance to the good estimators. So first, we are going to discuss about one by one here. First, unbiasedness. So unbiasedness means nishpakshabhatamu antaru. Unbiasedness. Unbiasedness is there is no biasedness. Unbiasedness is a property associated with the finite n here. Infinite samples, there are no need to take this one here. Only finite cases we have to take the unbiasedness. A statistic T, function of sample observations x1, x2, xn, is said to be an unbiased estimator of g of theta if expectation of t is equal to g of theta. Theta belongs to parametric space. Expectation of statistic is equal to parameter. Expectation of statistics equal to parameter. So that statistic is called unbiased estimator of the population parameter theta. G of theta is a function of theta. G of theta is a function of theta. Theta square, theta cube, 1 by theta, root theta, sin theta, like this here. So remark, if expectation of, mathematical expectation of this is called average. So this is called average. To test the unbiasedness, use the mathematical expectation techniques. So the mathematical expectation technique, the mathematical expectation of the statistic is greater than function of parameter g of theta. T is said to be positively biased. Is greater than g of theta, positively biased. If expectation of t less than g of theta, it is said to be negatively biased. So there are two important remarks. The amount of bias b of theta is given by b of theta is equal to expectation of t minus g of theta. This is called bias concept here. So write the bias values of the estimators. You have to use these techniques. Expectation of t minus g of theta. G of theta is a function of theta. So understanding purpose of the unbiasedness, here we have to discuss some examples here. All are live examples, very, very important examples for examination point of view. First problem. So now here xi follows Poisson distribution. Xi follows Poisson distribution with parameter lambda. Here, one thing here, in a theory of estimation and testing hypothesis, all xi's are IIDs. All xi's are IIDs. Remember one point here. Here I is equal to 1, 2, 3 and so on here. Now x1, x2, xn be a random sample drawn from this population of size n with parameter lambda. The sample is drawn from the Poisson population with parameter lambda. The sample has finite number of sample observations x1, x2, xn. Here we have to estimate the lambda, lambda square. So we have to estimate the unbiased estimate. We have to give the unbiased estimator of lambda square. These two are very, very important for the examination point of view. Now, first of all, here for any model here, first of all, we have to write the mean and variance. E of xi is equal to Poisson mean is not very, very important concept here. The properties of Poisson distribution. Mean of Poisson is lambda. So variance of Poisson also lambda. Now here is E of x square is equal to variance of x plus E of x whole square, shortcut formula. Easily we can find out this one. So that is lambda plus lambda square, lambda plus lambda square. Now here we have to estimate the lambda value using the function of sample observations. Here function of sample observations means n samples are drawn here. We have to construct we have to identify the function of sample observation. So here is first of all, I have to give the importance to x bar here. So x bar, expectation of x bar means summation xi by n here. Most of the cases here x bar is the good estimator for the lambda here. First of all, you have to check here. So 1 by n. So summation expectation of xi I is equal to 1 to n. That is 1 by n. Summation e of xi is equal to lambda. So here I is equal to 1 to n. Here lambda is a constant, n times here n lambda by n. This is lambda. So e of x bar is equal to lambda. Therefore, x bar is unbiased estimator of lambda. So first one is over here. So to estimate the lambda, use sample mean. Using sample mean, easily we can estimate the lambda. So x bar is the unbiased estimator of lambda. Now here we have to, so here we have to calculate the another one. One more estimate lambda square. For lambda square here, generally we have to take 1 by n summation xi square is a function identified here. By practice, usually you can also identify those such functions here. So this function gives the unbiased estimator of the lambda square here. 1 by n is taken outside, summation e of x square. Now that is 1 by n, summation I is equal to 1 to n. So e of xi square. Here expectation of xi square is what here? Lambda, lambda square plus lambda. Now this is constant value. Here is n into lambda square plus lambda dividing by n. N cancel. That is equal to lambda square plus lambda. Now our requirement is lambda square. Here is expectation of 1 by n summation xi square minus expectation of constant is constant minus lambda here is equal to lambda square. Already lambda is so estimated here. So x bar is the unbiased estimator of lambda. Replace lambda by here. So completely how to give the function of sample observations. This function does not involve any parameter, but in this case a lambda is already estimated. So with the help of the sample mean, easily we can estimate the lambda value. So x bar so is equal to lambda square. Therefore, so 1 by n summation xi square minus x bar is unbiased estimator of lambda square. It's very, very important for the examination. Dash is the unbiased estimator of lambda. So 1 by n summation xi square minus x bar is a unbiased estimate of lambda square. One more example. Several examples are noted here. That x1, x2, xn be a random sample from binomial population with parameter n and p. If n is known, so the unbiased estimator of p. There are two parameters here. N is a constant parameter, p is a variable parameter. P is always lying between 0 and 1. So x follows binomial n comma p. First of all, here the mean of binomial e of xi, that is equal to np. So now here is we have to estimate the p value here. So now in this case here, so x1, x2, xn samples are drawn from this binomial population with parameter n and p. So now we have next go to the process a of x bar. X bar is a statistic, a function of sample observation. You have to identify the you have to develop the one principle to identify the function of sample observation. So this is the suitable function of sample observations to estimate the population parameter p. Now e of x bar is equal to expectation of summation xi by n. So now he is 1 by n. So summation e of xi. So now here I is equal to 1 to n. So 1 by n summation I is equal to 1 to n. E of xi is equal to np. So 1 by n into, so n times here, n times n into np. This n cancel here. So now here remaining part is np. N is the degree of binomial. The n is the sample size. Don't confuse here. So now e of x bar is equal to np. So now expectation of x bar by n. So n is a constant value is taken into, so left side is x bar by n is equal to p. So now here this is a function of sample observations. So this is a principle identifying the function of sample observation. This using this function we have to estimate the population parameter p. So now x bar by n is unbiased estimator of p. Next, geometric distribution. Xi follows geometric curve P. P is unknown. Unbiased estimator of 1 by P here. So now here, expectation of similarly here, same procedure. For each and every problem, first of all, you have to, first two steps are same here. P of Xi is equal to 1 by P. P of X bar. P of X bar is equal to expectation of 1 by n summation Xi. That is equal to 1 by n summation E of Xi. I is equal to 1 to n. So 1 by n summation I is equal to 1 to n 1 by p, that is equal to 1 by n into 1 by p. N cancel, that is 1 by p. So now therefore x bar is unbiased estimator of 1 by p. So here we some doubt maybe happen in this situation here. What is the unbiased estimator of P? So unbiased estimator of P does not exist. Geometric distribution does not exist. Geometric distribution. Remember this point here. Unbiased estimator of P does not exist for geometric distribution. Is very, very important one. So problem example 4 here. Example 4. Xi follows n of u comma 1. I is equal to 1 to n. E is an unbiased estimator of 4. Dash is the unbiased estimator of u square plus 1. Same thing here. Normal population. Mean is equal to E of Xi is equal to mu. Variance of Xi is equal to 1 given in the problem. So now here E of x square is equal to variance of x plus E of x whole square. Here is directly is a normal population. So now here variance of x is equal to 1. E of x is equal to mu square. Now E of x bar is equal to expectation of summation xi by n is equal to 1 by n summation E of xi, that is equal to 1 by n summation mu, that is equal to n mu by n, that is equal to mu. Here is variance of x bar. So variance of x bar shortcut formula is there. So that is sigma square by n. Here is sigma square is what here? Here is sigma square is 1 by n. Variance of x bar is 1 by n. Now here our requirement is unbiased dash is the unbiased estimator of mu square here. We have to identify the one function here, 1 by n summation xi square. That is the suitable function to estimate the population parameter mu square plus 1. So 1 by n summation xi square is equal to, so 1 by n summation E of xi square, E of xi square, that is 1 by n summation, so mu square plus 1 already defined here, mu square plus 1. So now that is equal to n into mu square plus 1 dividing by n is cancelled. Therefore 1 by n summation xi square is unbiased estimator for mu square plus 1. But variance of x bar, this only for additional information is given here, how calculate this variance of x bar. But no need to take this variance of x bar first to estimate the mu square plus 1. So directly we can take the simple function is a precise format here. This is precise format to estimate the u square plus 1. General concept. T is an unbiased estimator of theta. T square is a biased estimator of theta square. This is a remark. So straightly how to take this statement. Here proof is there. I will here is so I'm going to discuss about this how it is true here. Expectation of T is given. T is unbiased estimator of theta. In this case, expectation of T is equal to theta. So now expectation of T square. We have to the T square is, we have to show that T square is unbiased estimate of theta square. Expectation of T square is equal to variance of T plus expectation of T whole square. So variance of T as it is variance of T plus this is theta square. So variance of T always greater than 0. So therefore expectation of T square so not equal to theta square because variance of T is greater than 0. So it's a positive value, but it is not equal to theta square. Therefore, T square is biased estimator of theta square. Biased estimator of theta square is very, very important. Direct statement or question for the nationwide university examination point of view. Next, problem 6. Here is a Bernoulli population. X1, X2, Xn be a random sample drawn from the Bernoulli population with parameter theta. So Xi follows Bernoulli 1 comma dash is unbiased estimate of theta square. So now Xi follows Bernoulli, E of Xi is equal to, so here is theta, variance of Xi is equal to theta into 1 minus theta, P into Q, Q is equal to 1 minus theta. T is equal to summation Xi, the statistic here, the function of sample observation. The sum of the binomial Bernoulli's follows binomial distribution n comma theta, n comma theta. So expectation of T is a Bernoulli variate. The mean of Bernoulli, T is a binomial distribution. The mean of binomial distribution is NP. Here is P is theta. So variance of T is equal to, variance of T is equal to n into theta into 1 minus theta. Expectation of T square. Expectation of T square is equal to, expectation of T square is equal to variance of T plus expectation of T whole square. Expectation of T whole square. Variance of T is equal to n theta 1 minus theta plus n square theta square. N square theta square. Expectation of T square can be written as a, by using partial fractions technique. So T square can be written as T into T minus 1 plus T. After simplification, this expression is equal to T square. Now this is equal to expectation of T into T minus 1, T minus 1 plus expectation of the L2 property applied here is equal to n theta minus n theta square plus n square theta square. Now expectation of T into T minus 1, T minus 1 plus expectation of T is equal to what here? There is n theta. Define n theta is equal to n theta minus n theta square plus n square theta square. Now n theta cancel. So expectation of T into T minus 1 is equal to, here is a common factor n theta. N theta is a common here for both expressions. Here n value n minus 1. Now here is, this can be taken as T into T minus 1 dividing by n into n minus 1 is a purely constant value taken into the left side. That is equal to, here is theta square is common, that is theta square. So now T is equal to, replace T by what here? Summation Xi. Summation Xi minus 1 by n into n minus 1 is equal to theta square. So therefore, summation xi minus 1 by n into n minus 1 is unbiased estimator of theta square. It's very, very important. So bit for the examination point of view. Problem 7. X follows Poisson theta. Now here we have to prove that expectation of minus k whole power x is equal to e power minus of k plus 1 theta. So we can say that minus k whole power x is unbiased estimator of e power minus k plus 1 theta. Is a function of parameter theta. So now here Poisson probability function p of x equal to in terms of with parameter theta here e power minus theta power x by x factorial. So x range here 0 to infinity. 0 to infinity. So now here expectation of minus k whole power x is equal to summation minus k whole power x into p of x is e power minus theta power x by x factorial. Here x range start from 0 to infinity. That is equal to summation x equal to 0 to infinity. Here is minus k whole power x theta power x. Powers equal base multiply here. Minus k theta whole power x e power minus theta by x factorial. So now that is equal to e power minus theta constant. Now x value substitute, expand this summation. That is 1 minus 1 plus minus k theta by 1 factorial plus minus k theta whole square by expectation of minus k whole power x is equal to e power minus theta 1 plus minus k theta by 1 factorial minus k theta by minus k theta whole square by 2 factorial plus infinity up to infinity. And now here e power minus theta, the sum is equal to e power x. So now here x is equal to minus k theta. E power minus k theta, that is equal to base equal powers adding. E power minus theta minus k theta. So now here is minus theta is taken outside, is k plus 1. So now therefore expectation of minus k whole power x is equal to e power minus theta k plus 1. K is positive value greater than 0. So minus k whole power x is unbiased estimator of e power minus theta k plus 1. Is very, very important bit. For example, k value 2. K value always greater than 0. Suppose k value 2. Minus 2 whole power x is unbiased estimator of, is a direct question, direct question for national wide universities. Minus 2 whole power x unbiased estimator of k value 2 here, 2 plus 1, 3, 3 theta. Is very, very important for the examination point of view. The next problem 8. Example 8. Xi follows exponential distribution. Xi follows exponential distribution. Expo of parameter 1 by theta format. So now the PDF is f of x equal to 1 by theta into e power minus x by theta, x greater than 0. Unbiased estimate of theta square. So here mean of exponential is 1 by theta. Here is parameter is 1 by theta. 1 by theta is equal to theta here. Variance of x is equal to theta square. Mean is equal to theta. Variance is equal to theta square. Immediately how to identify the function of sample variation. The suitable function is sample mean. E of x bar is equal to expectation of summation xi by n. So now, so this is E of x bar is equal to 1 by n summation E of xi is equal to I is equal to 1 to n 1 by n summation E of xi is equal to theta, I is equal to 1 to n, that is n theta by n, that is equal to theta. Now, therefore, x bar is unbiased estimator of parameter theta. Now here we have to theta square. So variance here is E of x bar square is equal to variance of x bar x bar is statistic. So this is suitable statistics for theta square. E of x bar whole square. This is a formula. So now E of x bar square is equal to variance of x bar. It is sigma square by n. Sigma square is what here? In this case, sigma square is theta. Theta square by n. The variance of x bar formula explained in the last video. So x bar follows normal distribution. The variance of x bar generally sigma square by n. So now here is sigma square is theta. Theta square by n plus E of x bar is already computed. This is called theta square. E of x bar square is equal to theta square is common. So 1 by n plus 1. So expectation of x bar square is equal to theta square into n plus 1 by n. Now, here is expectation of x bar square into n by n plus 1. Left side here is taken into. So, left side is a pure constant value. So, the remaining part of the right side is theta square. So, expectation of n x bar square by n plus 1 is equal to theta square. Therefore, n x bar square by n plus 1 is unbiased estimator of theta square. Is very, very important. Problem 9. Example. So now here is another population. X follows uniform distribution A comma B. Here is A is known value, unbiased estimator of B is dashboard. The probability function, so here is continuous uniform distribution. So that is probability function 1 by B minus A less than or equal to X less than or equal to B. Here A is a constant value, B is a constant value. Out of these two constants, A is known. We have to estimate the B value using the unbiased technique. Expectation of X is equal to B plus A by 2. So variance of X is equal to B minus A whole square by 12. Expectation of X bar is equal to here is remember one point here. E of X equal to B plus A by 2 by here sample observations. Function of sample observations. The suitable function is X bar. The E of X bar is equal to expectation of summation Xi by n. So after simplification, this value also B plus A by 2. So E of X is same as to E of X bar. Remember this point here. Shortcut. Don't take process each and everything is here. Now here is implies here E of X by cross multiplication. 2 is a constant value. 2x bar is equal to B plus A. 2x bar is equal to B plus A. Now A is a known constant value. So is also a 2x bar minus A is equal to B. Therefore, 2x bar minus A is a known constant value, is unbiased estimator of B. Unbiased estimator of B. So next example, example related to the discrete uniform distribution. Discrete uniform distribution. What is the unbiased estimator of Kaplan? Kaplan is the parameter of the discrete uniform distribution. In this case also, first of all, here property of the discrete uniform distribution, mean E of x equal to, you know very well, n plus 1 by 2. So E of x bar. E of x bar is same as to, for each and every distribution, E of x bar is same as to E of x. So directly you can write the n plus 1 by 2. So now cross multiplication. This is 2x bar is equal to Kaplan plus 1 by 2. Kaplan is the parameter of the discrete uniform distribution. Now we have to estimate using the function of sample observation. A suitable function expectation of 2x bar minus 1 is equal to Kaplan. Therefore, 2x bar minus 1 is unbiased estimator of Kaplan. Unbiased estimator of Kaplan. Problem 11. X follows hypergeometric distribution. Hypo of Kaplan, capital M, small n. Now here is E of x is equal to, so that is the main property of the hypergeometric distribution, small n into capital M by capital N. Now one more function is a requirement, x into x minus 1, that is equal to, so m into m minus 1, m into m minus 1, n into capital N minus 1, small n minus 1 by capital N into capital N minus 1. Here is small n, capital N are known constants. Here we have to estimate the unbiased estimator of m square here. For this process, we have to identify the suitable function of sample observations. So expectation of suitable function of sample observations for m square. For this process here, by cross multiplication, x into x minus 1, capital N is a constant value, already known value. So bringing to the left side by dividing by small n into small n minus 1. Small n into small n minus 1 is equal to m into m minus 1. M into m minus 1 is what? M square minus m. So expectation of x into x minus 1, n into n minus 1 by small n into small n minus 1. Here is bringing to this side here. Our requirement is m square. So now here this is extra value. This is bringing to this side. Here is capital. So now here is m square. That function of sample observation only involving with functions of x, functions of functional sample observation only. Here from this E of x equal to n, small n into capital M by n. So here we have to find out the m value. That is by cross multiplication, nx by small n is equal to m. Replace m by what here? So capital Nx by small n. So now this is the expectation of x into x minus 1, n into n minus 1 by small n into small n minus 1. So plus that is nx by small n. So replace m by this value. So now this is equal to m square. M square. Therefore, x into x minus 1, n into n minus 1 is a constant by, so n small n minus 1 plus capital N x by n. Here is small n is unbiased estimator of m square. That is very, very important. So it's very important for the National University Examination point of view. Problem 12. Example 12. Xi follows gamma distribution 1 by theta gamma n. Here is n is known value. N is a lambda. Here is known. one value. So now here is E of xi is equal to original formula lambda by A. Here is A is equal to 1 by theta, lambda is equal to n. So now n by 1 by theta, that is equal to n theta. So E of x bar is equal to immediately. E of x bar is same as to E of x. Very simple shortcut technique. So no need to take the lengthy process here. E of x bar is equal to n theta. Implies expectation of x bar by n is a function of sample observations, the suitable function of sample observation to estimate the parameter theta. Therefore, so x bar by n is unbiased estimator of parameter theta. Now here we have to estimate the, we have to give the unbiased estimator of theta square also. In this process here, E of xi square. E of xi square is equal to variance of xi plus E of xi whole square. So variance here, variance formula, variance of xi is equal to lambda by a square. Lambda by a square original formula. Here is lambda is equal to n by theta square, 1 by theta square. That is equal to n theta square. Now here is n theta square plus E of xi is equal to, E of xi is equal to what here? N theta. So n square theta square. So now here is that is equal to here is theta square is n theta square common. So 1 plus n. Immediately have to observe the identifying the function of sample observations to estimate the theta square. The suitable function is 1 by n. The suitable function is summation xi square. Is a required function that is equal to summation I is equal to 1 to n. So E of xi square, that is equal to summation I is equal to 1 to n. That is n theta square n plus 1. So now n into n plus 1. So summation I is equal to 1 to n theta square. Here is n into n plus 1. This is same as to n theta square. That is n square into n plus 1 into theta square. Expectation of summation xi square by n square into n plus 1 is equal to theta square. Expectation of expectation of summation xi square by n square into n plus 1 is equal to theta square. Some correction is there in this one. Here there is a wrong process applied here. On this one, I am deleting this one. This is wrong process. Up to this one is okay. To this one is okay. So expectation of xi square is equal to variance of xi plus E of xi whole square n theta square plus n square theta square. So n theta square plus n plus 1 here. Now expectation of suitable function. Identify the function of sample observations for theta square. So 1 by k samples, summation I is equal to 1 to k xi square, that is equal to some expectation 1 by k is taken outside. 1 by k is taken outside constant value. Summation I is equal to 1 to k samples. Already n is there here. N is the lambda parameter of the gamma distribution. Expectation of xi square 1 by k summation I is equal to 1 to k. E of xi square is equal to n into n plus 1 theta square, that is n into n plus 1 by k, summation I is equal to 1 to k theta square. Now n into n plus 1 by k, that is equal to k theta square. K cancel here. K samples are there. So now n into n plus 1 into theta square. This is the expectation of 1 by k summation xi square. Now expectation of 1 by k summation xi square dividing by n into n plus 1 is equal to theta square. Therefore, summation xi square by k samples n into n plus 1 is unbiased estimate of theta square. Gamma distribution. Finally, here another suitable, very important example, normal distribution case here. So now xi follows normal distribution mu comma sigma square. E of xi is equal to mu, variance of xi is equal to sigma square. X bar follows n of mu comma sigma square by n. E of x bar is equal to mu, variance of x bar is equal to sigma square by n. Already explained. Now here E of x bar is equal to mu. Therefore, x bar is unbiased estimate of mu. Unbiased estimate of mu. Here, x bar square is equal to variance of x bar plus E of x bar whole square. That is equal to sigma square by n minus plus mu square. E of x bar square minus mu square, bringing to left side, is equal to sigma square by n. So now expectation of n into x bar square minus mu square is equal to sigma square. Therefore, n into x bar square minus mu square is unbiased estimator of sigma square. Mu is known case. Mu is known case. Mu unknown case, expectation of small s square is equal to n minus 1 by n sigma square after simplification. Implies expectation of ns square by n minus 1 is equal to sigma square. So implies expectation of is treating as a capital S square is equal to sigma square. Therefore, capital S square is unbiased estimator of population variance sigma square. Mu is unknown case. U is unknown case. U is unknown case. So this is very, very important for examination point of view. So all examples are very, very important problems for the regional-wide and national-wide university examinations, so direct problems. So now, so here to solve these problems here, that concept of the unbiasedness is very easy to apply the, so any situations here. So this is unbiasedness is complete, but some remarks are there here. Sample Rth moment. Rth moment is unbiased estimator of the population Rth moment if it exists. So moments are exist here. We can take this one. Expectation of MR dash equal to MR dash. So MR dash is unbiased estimator of the unbiased estimator of MR dash. MR dash is equal to MR dash formula summation x power r by n. So MR dash formula is equal to summation x power r into p of x for discrete random variables. Continuous random variables minus infinity plus infinity x power r into f of x dx. So unbiased estimators need not be unique. Very, very important one. Unbiased estimators need not be unique. If for T1, T2 are the two unbiased estimators of parameter theta, T3 is equal to alpha T1 plus 1 minus alpha T2 is a linear combination. So convex combination of T1, T2. So is always T3 is the unbiased estimator of parameter theta. So convex combination is given that statistic is a unbiased estimator of parameter theta. T3 is the convex combination of T1, T2. One more example. So x follows uniform distribution 0, comma theta. So now f of x is equal to 1 by theta. So x lie between x lie between 0 less than or equal to x less than or equal to theta. Now here is the mean of e of x is equal to e of x is equal to b plus a by 2 theta by 2. So e of x bar x1, x2, xn be a random sample drawn from this population. E of x bar is equal to theta by 2. Same thing here. Now directly we have to estimate 2x bar is equal to theta. Therefore, 2x bar is unbiased estimator of population parameter theta. The general statistics concept is general samples x1, x2 are drawn from this population. From this population continuous uniform distribution. So directly 2x bar is unbiased estimator of population parameter theta. Now one more example here based on order statistics here. X follows uniform distribution 0, comma theta. Now there is letter x1, x2 and so on. Xn be a random sample drawn from the above population. Now consider the order statistics. Already explained here order statistic in last video. Order statistic x1 order less than or equal to x2 order less than or equal to and so on xn order. Here x1 order is the minimum value, minimum of xi. Xn order is a maximum of xi. So this is denoted as x1 order. This is denoted as xn order. So now here we have to consider the expectation of xn order. This is very, very important for the examination point of view. Expectation of xn order is equal to n by n plus 1 into theta. But xn order is a biased estimator. Xn order is biased estimator of parameter theta. So now here in this case, to get the unbiased estimator, we have to identify the function of sample observations. So function of sample observations or order statistics observations. In this case, bringing to left side here, n by n plus 1 is a purely constant, n plus 1 by n. So xn order is equal to theta. But in this case, at a new statistic n plus 1 by n, xn order is unbiased estimator of parameter theta. So for example, here is n is equal to 3. So now in this case, 4 by 3. So xn order is unbiased estimator of parameter theta. Similarly, n is equal to 7 in this case. So now 8 by 7, xn order is so unbiased estimator of parameter theta. So unbiased estimators need not be unique. This is a suitable example. Need not be unique. So unbiasedness is over. All examples, concepts, so several models are explained